So this is cryptography. Whoa, and something weird happened. All right, there. All right, and so we're down to keyed hashing. And my demo today is going to be RSA, the next thing to come up. So let's take a look at keyed hashing. So message authentication codes are things you sign messages with that are more than just a hash. They are keyed hash, which we'll talk about. And they use pseudo-random functions, and we'll talk about the structure of keyed hashes and how things can go wrong. So a keyed hashing, now you can calculate the SHA hash of a method, SHA-1, SHA-2, whatever, no secret values involved, and you could do that to verify that a copy of the message has not been altered, but it's not a signature. Keyed hashing forms the basis of two algorithms, message authentication codes and pseudo-random functions. And the message authentication codes give you more than just a signature to show the message has not been altered. They also prove that you know who the author is, because they have both the message and a secret key. So this tag is more than just a hash. It's the hash of a key plus a message, so it proves both that the message has not been altered and that you are the holder of the secret key. So it's authentication and integrity. So that's the game. All right. And so they're used in a lot of secure communication, IPsec, SSH, TLS, 3G and 4G telephony, encrypted packets, but didn't use a MAC, and that meant you could modify the packets on the line because you could alter the packet and that would create static. So, all right, now, so the security requirements of a message authentication tag is that you shouldn't be able to create a tag without knowing the key. If you were, that would be a forgery, and you want a system that's unforgeable if you can't, in practice, create a forged message without knowledge of the key. Now, you might have a known message attack. This is the kind of thing that worked against WEP. There are often, if you look encrypting network traffic, you can often guess what network traffic is, like the ARPs. And so then you could passively collect messages and tags and try to find the key. All right. Chosen message is even more of giving the attacker more of an advantage. This is where you can send up messages of your choice and it will encrypt them. You can examine the encryption. And so if you can survive this, that's a very strong algorithm. This is what you typically do to test your MAC algorithms. You might as well have good, strong MAC algorithms. You make one that you can't even break with a chosen message attack. That would be the best one to have. And they've got those. Replay attacks, by the way, you can't do anything about. All there is a private key and a message, and so you could replay the same message with the same tag, and it would pass the test, of course. There's nothing to prevent that here. And therefore, if you want to prevent that, your protocol has to include in the message a number, which is counting up, so you'll notice that the replayed message is not in sequence. This is a fundamental problem to be aware of. All right. Another way to do it would be to have some kind of challenge response, but that's not how they did it, just a message number. So pseudo-random functions are one of the things you can create with these things. So you use a secret key to return a pseudo-random function of key and message, and the output will look random, so you can use this to create pseudo-random bits. And key derivation schemes work this way, like PBKDF2 and scrypt and bcrypt. These are systems that will, PBKDF2 is the one specifically targeted for this, although I think scrypt and bcrypt work essentially the same way, but that stands for password-based key derivation 2, and we'll use it in the projects. This is why what happens if you log in to like an iPhone, you type in a password, and then it decrypts your phone. So it needs an encryption key, which is going to be something like 128 bits of AES, and it's getting that from a password that's a shorter phrase, and so it does that with a key derivation scheme, which is essentially just a hashing. So that's a way. All right, identification schemes also use this. You can get a random challenge and then add the challenge to your secret and hash it and send it across, and that can also use a pseudo-random function. So you can use these things. 4G telephony uses them to authenticate a SIM card. TLS uses this to generate key material from a master secret and a session-specific random value. And we'll use it in the projects. Hard disk encryption uses it and so on. All right, so in order to have a good pseudo-random function, it should look completely random. The output should look indistinguishable from random bits, and therefore it's fundamentally stronger than MECs need to be. A message authentication code does not have to pass this test. All it has to be is unforgeable. It doesn't have to appear random. That is not necessary for message authentication code. So you can create keyed hashes from unkeyed hashes. And here's what people often do. They just prepend the key to the message and then hash it. So you could use something like SHA-1, have key, and then add the message after it. Now, if you did this, it would be vulnerable to length extension attacks because if you had message 1 followed by message 2, if you know this, you could just add message 2 and run the hash function. So that's a problem. If you know one, remember you can replay a message, you'd be able to create another valid message key pair by just adding more message to the end of this one and then calculating the hash, which you can do because you can take the hash here and you can extend the hash because SHA works by cycles. A block of data, another block of data, another block of data. You can add additional blocks of data to this hash without knowing the internal messages. So SHA-1 and SHA-2 are vulnerable to that, but not SHA-3. So there's another one too. If the key is 123ABC and the message is DEF00, or the key is 123A and the message is BCDEF0, you're going to get the same answer because you didn't put a delimiter between the key and the message. So that's another insecure aspect of this. There are certain ambiguities. So Blake 2 and SHA-3 included a keyed mode to prevent this. And another fix, of course, would be to include the key's length in the hash. Barely better than adding a delimiter. Then you'd always know how much of it is key and how much of it is message. These seem like simple things to go wrong, but they are defects in the systems we have now. Another system is the secret suffix. Just take the message and put the key at the end. That will also prevent length extension because this is what you'd have to do to get the hash of a longer message, and you can't deduce that from knowing this. So it's kind of silly. Secret suffix is much better than secret prefix to avoid length extension attacks. All right, but if there's a hash collision, then the tags can collide too, which is reasonable. I think there's no way to get around that, but anyway, that is a limitation of it. So there's another HMAC construction, more secure than either of those, used by some of these things like IPsec, and that's this one, where you take the key and XOR it with OPAD, and then you take the key and XOR it with IPAD, and then you have 2 layers of hashing. And so you hash this, and then this hash is inside that hash, and then you put the message here. So you have taken the key, and you combined it with the message, but you combined it in such a way that there's no way to do a length extension or anything with it. This is considered the best system, and the OPAD is just a series of 5C bytes, and the IPAD is just a series of 3/6 bytes. Not obvious why you choose those particular numbers, but certainly this will have the effect of making it impossible to take this for one message and deduce what would be for another message without knowing the key, which is the point. All right, so your hash function has to be specified. Well, everything we said so far would work for any hash function, but you would specify, like AkeMash, SHA-256. You choose one of them, and so you take the key, feed in some original state, H0, that would create H1, then you feed that in as the, with another block of message and compress it, and on you go. This one, you feed in the whole message at once, compress it, and go through various stages. Here's the key. This is the system we had. Key XOR IPAD is used as the key here, and the key XOR OPAD is used as the key here, and the 2 are combined. So you have 2 hashing processes, one inside the other, and the key is used twice. That's the system used for the more modern ones. And so there are generic attacks. You can forge an HMAC tag from a hash collision, of course. If you find a hash collision, to want to find one of these in brute force, you would have to do 2 to the n over 2 calculations, which we talked about before, the birthday paradox. So you'd have to do up to the square root of the number of possible hashes. And therefore, all right, so that's the brute force attack to give you some measure of its security. And so if the n is larger than 128 bits, it will be essentially impossible. You'd have to do 2 to the 64 calculations and store 2 to the 64, which I think has been done. So I'm not quite sure why it's okay for the length of the hash to only be 128 bits. I'm quite suspicious of that. I think that's MD5 and even SHA-1. Now all the hashes are 256. So I'm thinking you want it to be at least 256 bits these days, but I'm a little confused about this. In fact, we're not in a hurry. Let me bring up the book and see if I can figure out what they said there, because I thought you'd need 256 bits, like SHA-256. A generic attack against hash-based MACs. Let me just bring this up and see if I can find out what happened, because now I'm not convinced I understand it. Textbooks, all right. Right, maybe I don't have this book on this machine. It's serious cryptography. There we are, okay? All right. I don't want to synchronize. I want to find chapter 7. All right. So all right. So a generic attack. All right, it'll be around here. I don't know what this 128 stuff is. Okay, HMAC, okay. Two to the n over 2 tags, right? If the hash lends itself to linked extension, yeah. There, the effort becomes infeasible as n grows beyond 128 bits. What is n? If the digest is n bits, you can find two messages such that the hash matches by requesting 2 to the n over 2 MAC tags. Okay, that's the birthday attack. If it has the linked extension, you can use M1 and M2 to forge MACs. All right. Oh, I see. I think I understand it. The idea is you could find a collision. If your hash was only 128 bits long, you could find a collision. But in order to forge an attack, you would not be able to do that, although I don't quite understand why. Well, that's as far as I want to go to. I don't understand how 128 bits could be enough. I have to read that again and try to understand what they're talking about. But anyway, I don't think anybody's using anything as short as 128 bits anymore these days. So, what's that?
Right, so basically it's saying like if the bits are like 128 or larger, then it's infeasible to forge.
That's what they're saying, but I don't understand why, because you can find collisions if it's 128 bits. And if you found a collision, why isn't that a forgery? But that's why there's something about the forgery which would be harder. That's what they're saying. And so even if you find a collision, the step to go from a collision to a forgery would be impossible for 128 bits, they say. And I don't quite understand why that's true, but it might be.
Could be a typo.
What's that?
Could be just a typo.
Just a psych-up?
A typo.
I think it's true. I'm just not understanding. I don't understand exactly what this step is from a collision to a forgery. Can forge an HMAC tag from a hash collision, but it'll require. That's why I don't quite understand how you do the forgery. So I could go and dig through it, but I'm not that excited by it. I think I'm not going to struggle anymore with that detail. Let's try the Kahoot. Oh, let's see if any comments. No comments. All right. I've been through this many times, and I've updated these slides twice this semester, and still I can never quite understand every bit of it. It's the subtleties I can't remember. Anyway, I'll carry on. Right. All right, so which system doesn't have a Mac? Yep, that's 4G. Doesn't use a Mac. All right. All right, what's the most successful attack against a Mac? Replay attack is trivial and it works. There's nothing to prevent you from reusing the same message and same tag. It will pass.
Yeah, they put a rule so you can't do it 20 times.
What's that?
They put a number on the message so that you can't replay it.
Right, you'd have to add something outside the MAC system, like adding a sequence number there to prevent that, yeah. All right, switch hash is not vulnerable to length extension. SHA-3 is the only one. Kind of funny. That's why it might be one reason to move to it, although nobody's moving to it yet. Pretty much everybody's moving from SHA-1 to SHA-2, but so far I haven't seen anybody bother to move to SHA-3. Nothing about it is motivating them, but this is a feature.
You should get into a link extension attacking market.
If there is, apparently this isn't a big problem. But anyway, that's always the case though. When they have a system, then they develop various problems. They develop a new system and it doesn't have the problems. But until it really matters, nobody's motivated to upgrade their stuff. Until there's some attack that actually costs them money. Which makes sense, really. All right, which system is vulnerable to linked extension? All right. The secret prefix, that's the problem. If the secret comes first and then the message, then you could just add more message and it would work. The secret is included in the hash that's already been done. So the secret prefix is the one that has linked extension for the HMAC itself. All right. Luca. That's you? Good. All right. All right, so let's take a look at some more of these things. All right, so we're going to create a keyed hash from a block cipher. This is what CMAC does. So block ciphers, remember, compression function and many hash functions, built from a block cipher. And so if you remember that to our block ciphers, here's the Merkle-Damgard construction where you feed in blocks of message data. You have an initial value, you feed in the message data and run it through the cipher, and then you feed in another block and use this one as the output for the next one, and on you go. This is the Merkle-Damgard construction, which is very much like CBC, AES, and then you just keep the final output as the output. So you have a small output. Instead of getting the whole encrypted message, you just take the last block of encrypted message, which works as a hash function. And this is what MD4, MD5, SHA-1, and SHA-2 all do. And so use a block cipher to build a compression function. And this is a construction where you take the input from the previous block and you use it as the IV here, and you also XOR it here. And the point of that is now you can't use a decryption to reverse it. So these are some things from a previous chapter we talked about. And so now the compression function is often built on a block cipher. So your 8-mask can be built on SHA-256. CMAC uses only a block cipher. It's less popular than HMAC, but it is an option. It's used by Internet Key Exchange, which is part of IPsec, which is considered to be very secure. It's very complicated cryptography, but it's considered very secure. So remember, we talked about CBC-MAC, where you feed in the IV and the plain text, you encrypt it, and then you use the output of this one as the IV for the next one, and so on. So this is one way to do it. You start with an IV equals 0, then you encrypt all your stuff, and you only keep the last block. This is a hash function, and that's a CBC-MAC now. You have a key, which is not shown here. That is not just a hash function, but it's a keyed hash. It includes using the key for each of these encryptions, and it includes all the message. So that is CBC-MAC. That was the system. Now, CBC-MAC has weaknesses and was improved almost 20 years ago to make CMAC. So you can break CBC-MAC because of the same old problem, this XOR operation. So if you know the tags T1 and T2, you have the two tag messages for two single block messages, M1 and M2. Then, if the tag of the 2 message is also the tag of this message, M1 appended to M2 or T1. But the problem is that just like when you attach cipher block chaining with padding Oracle, it was this XOR operation here that made the trouble. if I go back to here, remember this, we were able to take, if all you know is ciphertext, you can take that ciphertext, and if you change one block here, it will just change 1 byte here because of this XOR operation. So the decryption step is vulnerable to a padding oracle attack because of this simple relationship between the ciphertext and the way you calculate the next plain text in decryption. And it's the same kind of flaw here. This is too simple. The IV is exactly the same. So if you know the two tags, then you can combine those two tags and create, you can forge a message and a tag. You can forge the tag for a message which combines the two messages you don't know. So even though you don't know M1 or M2, but you only know T1 and T2, you can forge another message that will have a valid tag, and it will be this combination of the messages. And therefore, in the first place, you shouldn't be able to forge any kind of valid tag. That's a flaw. In the second place, even though you don't know what these messages are, in practice, the fact that there's a simple combination of them might very well mean that you could arrange something here, like a meaningful string. Anyway, it's very much like the padding oracle attack. That's a flaw in CBC MAC. So to fix it, you do the same thing you did with AES. You don't use the same key over and over. You may use the key to create key 1 and key 2, and now you encrypt the last block with a different key. That does it now. Now this process is not so simple, and so if you have multi-blocks of message, you use the original key and just use a different key 1 for the last step. And so if the message fills the last block exactly, use K and K1, and if it doesn't, then you use padding and use K and K2. And so the point is, that's something we talked about before. If the last step is different, then you're not going to be able to combine two of these and make a valid longer one, because this step that's different has to always be at the end and not in the middle. So it's a simple way to improve it. And it's the same thing we saw with AES, where you don't use the key over and over, you use a key schedule. You keep changing the key for each round to avoid the same kind of problem. All right. So these use hash functions and block ciphers to build pseudo-random functions. Now, all of these are taking hash functions and block ciphers to make a pseudo-random function, and that works, but it turns out to be very inefficient. The hash functions have much more strict security requirements, and the encryption process is much more strict security requirements. You could make a faster MAC use case by making an algorithm designed for a MAC that does not pass all the statistical tests necessary for encryption or hashing. And that's what we do here. So Poly 1305 is optimized to run really fast. This is used for HTTPS and OpenSSH. And it's a universal hash function. It's a special hash function that is much weaker, but it has the security things you need for a tag, so it's not collision resistant. It uses a secret key and a message, and the only security requirement is that if you have two different messages, they'll have two different tags for a random K. It does not have to be pseudo-random. It doesn't have to be white noise, like pseudo-random function. This is the property you need. You don't really need generic collision avoidance. And so this is the simple function. It's just key and key squared and key cubed up to key to the end. It's just a polynomial in the key mod p. And so the weaknesses are the key can only be used once, and otherwise an attacker can solve two occasions like that and solve for the key. And so here's another way to build a MAC from a universal hash function and a pseudo-random function. And the point of this is you're not reusing something that was designed for a different purpose. You carefully design something that has only the statistical properties you need. That makes it faster. So it is secure. If UH is a secure universal hash, the pseudo-random function is a secure pseudo-random function. Each nonce is used only once for each key, and the output values are long enough. So that is Poly 1305 AES. Much faster than HMAC, only computes one block of AES, and so on. All right. It's as secure as long as AES is, and AES seems to be perfectly fine. Nobody's found any holes in it yet. There's another one called SIP hash. Poly 1305 is optimized for long messages. For small messages, you don't even need that. There's a simpler thing called SIP hash, which you can use for short messages. And it just has a cycle like AES, has these various rounds of you're going through combining XORs, additions, and word rotations. So again, just a faster, more efficient hashing algorithm to be used just for message authentication tags. So things that can go wrong. You can have verification. There. So timing attacks. You can have side channel attacks where you target the implementation. This code, for example, will return faster if the first byte is incorrect. It's trying to decide if your MAC is correct, so it calculates the first byte, and if it's wrong, then it doesn't bother to test the other bytes. So therefore, it will, this is the problem. All the efficient code is not time constant. It looks for shortcuts and takes the shortcuts, and that you don't want that. You want constant time code if you don't want to have a timing channel leaking out information. That's a problem. And that's why I say that for AES, the better solution, which is what we're all using, is special hardware just to do AES, where it goes right through and it always takes the same amount of time no matter what the key is. It doesn't do some kind of algorithm like this. It just goes right through the layers of transistors. All right, and then if they get the internal attack from a side channel attack, then things that are sponges, like SHA-3 and SIP hash can fail. So it's a thing to know, but of course there has to be some limitation in security. And this point, if you have some kind of leak of some of the internal secrets, they're all going to fall to some extent. So that's not too serious. Neither of those are too serious. Anyway, that's the more advanced ones. Let's try another Kahoot. Yeah, I would. It's getting too hot. Don't know why it's getting so hot in here. I guess I better wait a few more seconds. No, I don't blame you. I feel the same. Oh, I think they fixed the heater in the building, so now I've turned it on too much. This is what they do. The heater was broken for like a year and it was freezing. Now I guess they fixed it, so now it's too hot. That's like, well, what I heard is they have like $1 million central heating system controlled somewhere and it's never worked from the day they put it in. Anyway, it's City College. You get used to this stuff. All right. Yeah. All right, so a hash function that is not collision resistant. That's the universal hash function. That's what it is. It has enough good properties to make message authentication tags, but it's not collision resistant. All right, which one is fastest for long messages? Poly 1305. All right. All right, which one is best for small messages? SIP hash, all right. All right, which one uses a block cipher, but only for one block? Poly 1305, AES, it only does one block of AES calculation. That's part of why it's fast. All right. Good. All right, I'm going to stop the recording.